Doug Littrell again. Today is June 6th, 2017. This is video number 7. I did something this morning I've been wanting to do for quite a while and haven't taken the time. Tried to determine how, what the period of Jupiter would be if Jupiter were at Mercury's distance orbiting the Sun. Okay, according to orbital mechanics and the equations used for that, right now, all bodies, regardless if it's Mercury with this certain amount of mass or Jupiter with this, what is it, 114 billion times more mass than Mercury? Okay, according to relativity and the present orbital mechanics on this, which are used, which don't affect how we, not this, that part doesn't really affect how we accomplish missions in space. Okay, this is just on the side, and it's also wrong. Okay, but anyway, supposedly, according to relativity, okay, Jupiter, if Jupiter were at Mercury's distance, it would orbit at the same orbital velocity, have the same period as Mercury. Okay, now I have an equation for finding this is related to the gravity assist or gravitational slingshot concept, which is completely valid, of course, very true. And we use that all the time in space, our scientists do with spacecraft. But anyway, this is not that, but it's related to that. When a body comes by something like the sun, say, and it's captured, okay, it doesn't fly off in a parabolic track like a spacecraft is intended to when it gets added velocity by going near a planet, okay, and then it flies off because it's not captured. Okay, this is why when a body is captured, does it make a circular orbit sometimes, or near circular orbit, as opposed to another one that makes a highly elliptical orbit. Now, Mars orbit is fairly elliptical. So why is that compared to like Venus's orbit that's much more circular? Okay, it has to do with, it's very intuitive, okay? It has to do with too much velocity for, say, Mars, as opposed to what Venus had when it was captured. When it was captured relative to the sun, it had Venus had less velocity, and it also had, but another factor is it had more mass, and more mass helps it to be captured because it's more attractive than Mars, and so it Mars would have tried to travel away from the sun. It had maybe a little more velocity when it was captured, or it had not as much mass. But those two factors are what is what makes one orbit more circular as opposed to another orbit that is more elliptical. Now I have an equation for this. I came up with it in 2015. I don't have the numbers perfectly fine-tuned yet. There's a couple of new numbers, numerical values in it that need to be fine-tuned. Okay, but this morning, what I've been wanting to know, okay, and I've been talking about, I talked about it at Rockfest a little bit, but I hadn't done this yet. And how the question is, what would be the period of Jupiter if it were orbiting the sun at Mercury's distance? Now, I thought because the Kepler telescope has already recorded how there are some large planets, quite a bit larger than Jupiter, maybe several, I don't know, 2 or 3, 4 times larger than Jupiter. I'm not really sure, but we've already found, let me back up here. We've already found solar systems, at least one, where the Mercury is far away from a star compared to all of its planets that orbit it. Believe it or not, there's some stars that have planets that are orbiting it right next to it and in close range, and they're zipping around that thing in a ridiculous rate. We've already seen what I was going to say a moment ago, how that there's some giant planets, much larger than Jupiter even, that their orbital period is 3 days. They go around. Now those are all close in. To us, Mercury seems close in, but Mercury isn't nearly as close in as a lot of planets in their solar system. Okay, but still, okay. Now I thought Jupiter and Mercury's orbital path around Mercury's range, I thought that it was going to be, you know, in the single digits in days as for its orbital path, but I was wrong. Okay, according to, if you take, let's see, Mercury's mean velocity in meters per second, you convert that to miles per hour, you come up with 105,945 point blah 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 miles per hour. Okay, now the next thing you need to know is you want to take Mercury's period, which is 88 days, or it's more technically or more accurately 87.969 days. Okay, you take that. Well, first of all, you need to get miles per hour into miles per day. So you take 105,945 blah 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 point blah 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 miles per hour, and you just take it times 24. You come up with, let's see, that's like 2.5 million or so miles per day. Okay, then you take that times the period, because it's 88 days, or 87.969 days. And then you come up with a number that is, let's see here, like 2.2 billion, you know, there's a number there with point, decimal point, and characters after the decimal. But anyway, so it's about 2.2 billion miles per 88-day period by Mercury. Okay. Now all you need to do is take that number and insert Jupiter. Let's see. So, you know, how fast would Jupiter? Well, see, I've already figured this out on this sheet. Anyway, this is an early copy. Okay, I've got a number. In 2015, I already broke this down with my equation, and I figured that Jupiter at Mercury's distance would be going 1,700,790 meters per second. Now, when you convert that to miles per hour, it's 377 miles per hour. So I've already got this number on this sheet, on this print, of 3,878,000 basically miles per hour that Jupiter would be moving its velocity were it at Mercury's distance. So all I had to do was take that and take that velocity and insert Jupiter into Mercury's distance over its orbital path in a in one complete period. one complete revolution around the sun. And it comes out to 57.67, a little over 57 and a half days. Okay, I'm glad to know that now. It's not as extreme as I would have estimated. Um, it's, Jupiter would have an orbital, or excuse me, it would have a period of a little over 57 and a half days were it orbiting at Mercury's distance. And that's all I've got today for video number 7. Okay, one more note about Jupiter orbiting at Mercury's distance, okay? Having a little coffee this morning. In this solar system, what I determined, okay, I about pulled my hair out in 2015 when I was trying to figure out what's going on with orbits. You come up with all kinds of exotic formulas or equations. I tried a bunch of them. There's no way, I'll tell you right now, that the way things are figured, that the mass of M2, okay, in the case of the sun and the planets orbiting it, M2 represents all of the planets that orbit the sun. M2 in the equation. M1 is the sun. All of those are calculated presently. And this was including whatever Einstein was working with in his time. Okay, as if all of these, regardless of, and that's what relativity says, regardless of mass, they're going to travel the same velocity. That's false, okay? Anyway, what I found out in 2015 and realized after beating my head against the wall almost, trying to find an equation with the numbers that are out there for the solar system, which are good numbers. But what's happening is perturbation. What you got to have is each one of these planets orbiting a star like the sun alone with nothing else perturbed. Then you would know what's really going on with orbits. That's what it takes. All of these planets are on an orbital plane. How did they get in orbit? They didn't coalesce. The ones that coalesced here did not coalesce on that plane. That didn't happen. They were every which way around the sun coalesced. They pulled into the plane the same way Saturn's rings pulled into a plane. Whatever crashed and made all those ice and rock particles in Saturn's rings, that was a mess too, and it all by gravity pulled into a plane. There's gravity pulling to these little things one to another, and given enough time, they make, they're orbiting and they make a plane, a disk. And same thing with the planets that coalesced around the sun. They eventually pulled into a plane by gravity. They pull to one another. Okay. They also skew the numbers so that you don't know what's really going on with orbits. Some are pulling one another out, keeping one another out farther than they would be if they were orbiting a star like the sun alone. This is what's going on with orbits. And anyway, so that's something else I needed to mention. If now, in my view, Jupiter will eventually move in close. All of these orbits are going to close down eventually, and they will be orbiting much closer to the sun than they are now. Eventually, it depends on if given enough time, how long the sun lasts before it becomes a red giant, then a white dwarf, and all that. But that's all good stuff. All right, but if Jupiter were at Mercury's distance, right now, and then you had all these planets outside of it, okay, you would have to account for all of the perturbations that make things artificial, in a sense, from what they would be were these planets orbiting alone. in their own solar system with their own sun. Okay, so you know, this perturbation, it skews everything. Okay, this is what's going on. So when you get Jupiter down near the sun at Mercury's distance, you need it to be alone. So when I say, okay, it's orbiting at Mercury's distance, now if Jupiter were at Mercury's distance, it's so influential that it would change. I mean, it's going to bring Mars in when it comes in. Okay, gradually, it's going to pull. It's pulling Mars out right now. It's going to Mars is going to do whatever Jupiter does. Okay, when Jupiter gets in there, it's going to mess up the Earth and Venus. Okay, so when I say Jupiter is at Mercury's distance, okay, really, I'm really talking about Jupiter orbiting the sun alone. Okay, let's just say that Mercury isn't that perturbed. It probably is, but anyway, all of this has tremendous influence on orbital velocities, and it's why they all seem to be as if it doesn't make any difference what the mass of M2 is. Okay, I needed to make that point with this video. Morning, June 7th, 2017. Great morning after the great walk-off victory by the Kansas City Royals last night. Really enjoyed that. Mike Moustakas hit a dramatic 2-run homer in the bottom of the ninth. Really fun to see. Whit Merrifield also had a game-tying 3-run double prior to that. I can't remember if it's 7th or 8th inning, but anyway, the bullpen did a good job. One note, real quick note, no matter what you do, I mean, we love Salvador Perez here, we like Lorenzo Cain, but I think the priority of the city regarding the Royals is that they keep Eric Hosmer and Mike Moustakas. I think that should be a priority. Whatever you got to do to keep those two guys, I think that I speak for a lot of people that that's what we want here. Okay, moving on from that. I made a mistake yesterday. I just forgot to convert the 3.8 million miles per hour that my equation supplied, which I worked on in 2015 for months and months and months. After I tried a lot of other things first with orbits, but anyway, when I came up with that, and everything is in that equation, everything is very logical, nothing exotic in that equation. Anyway, I came up with the value that Jupiter would have a velocity of 3.8 million miles per hour. Anyway, it needed to be converted to miles per day. You just take that times 24. Then you divide it. I always find the distance of the orbit, the complete orbit, or that period, say, of Mercury. And so you divide that number after you take 3.8 million times 24, and you divide that distance by that number after you multiply 3.8 times million times 24, and it comes out to be 2.4. That I had told people at Rockfest, I thought that Jupiter probably would orbit in 4 or 5 days at Mercury's distance, and it turns out it's a lot more dramatic. Yesterday, came out with a figure of 57 days. I should have known that was fishy. You can figure this another way. Mercury's mean velocity is 47,362 meters per second. When you convert that to miles per hour, it's 105,945 mph. Okay, Jupiter's alleged velocity at Mercury's distance, alleged by my equation, is 3,878,377 mph, which is over 36 times Mercury's velocity. Now take 88 days, which is Mercury's period, and divide that by 36, which equals 2.4. And there you have it. Okay. One more thing. I always say that these planets need to be in a solar system alone, orbiting a star like the sun, in order to see the relationship between M1, the star, and M2, the primary, and the secondary M2, the planet. That the mass of M2 has a enormous bearing on the velocity it has at its distance. And so they need to be alone. Right now, see, Saturn is pulling Jupiter out, and it's also, Jupiter's going a lot slower than it would according to its mass were it orbiting alone at its distance that it has right now. But Saturn, Uranus, and Neptune are pulling Jupiter out, holding it back. It's actually slowing. Those bodies are going very slow where they are. That pulling slows Jupiter down as well, and also holds it out. But it makes our solar system last a lot longer than it would if these bodies were, let's say if the Earth were alone and we were on the Earth alone in a solar system. The Earth would close down into a centripetal path a lot sooner than what we have here in this solar system. Anyway, Jupiter will eventually close, even despite all this, if the sun lasts long enough before it becomes a red giant. Of course, then after that it turns into a white dwarf, in which all the planets not destroyed by when it's a red giant would be lost when it becomes a red dwarf. They would wander off and become interlopers and be captured by other stars and other places. But anyway, Jupiter, if it has enough time, it will close in eventually, and reach Mercury's distance if it has enough time. And when it does, it will bring Mars in with it, and Mars will behave like a Trojan relative to Jupiter. Anyway, I won't go into any more on that right now.